Okay guys, so in this one we're gonna prove, in this video we're gonna prove the convolution theorem. No, convolution theorem. Okay, so first I need to recall, we have the definition of convolution. So if f and g are L1 functions, that means the integral of f is less than infinity in absolute value. Okay, we define the convolution of two functions. So you see, you have multiplication, you have subtraction, you have division. Now you have a new operator. It's called convolution, and it's 1 over the square root of 2 pi in the integral over the real numbers of f x minus theta g theta d theta. Okay, that's my convolution. My convolution is an integral of the product of the two functions, and one is kind of has a little translation, or is shifted. Okay, so that's my definition of convolution. So this is the theorem of convolution, the convolution theorem. Convolution theorem. So if the Fourier transform of f of x, let's call it f of k. Okay, and the Fourier transform of g of x, we call it g of k. Okay, then the Fourier transform of the convolution equals the product of the Fourier transforms. Okay. So we use this in the heat to solve the heat equation, to solve the wave equation. Okay, so this is very important. Or equivalently, another hard word for me. I think it's this kind of too dark. Is that the one I'm using? The Fourier transform inverse of fk times g of k equals f of x convolution g of x, and this is basically 1 over the square root of 2 pi integral over the real numbers f x minus theta g theta d theta. And on the other side, the Fourier inverse is the integral. Well, let's put it here. This is the integral over the real numbers of e to the I k x f of k times g of k dk. Okay, so that's basically what we have. Make it something thinner. I don't know, it's so dark. Okay, so so yeah, recall that the Fourier. So just to make sure people is following me, recall the Fourier inverse of f of k, but we define it like 1 over square root of 2 pi integral of e to the ikx, and this is positive, the real numbers, and then f of k dk. Okay, so we're just recalling that. So you remember. Okay, so here is the proof. The proof is very nice, very simple. Well, another notation for Fourier transform is the hat. Okay, so it's a possibility called also this f hat. Okay, so just get used to. So those are three notations for Fourier transform of a small f. So it could be capital F of this weird f of f, or just hat of f. So I'm gonna use just the hat for this proof. That's because it just gets easier to move the hat all over. Okay. So first, let's start over here. We're gonna start here. So the Fourier transform of the convolution of f and g is using the other notation, the convolution of f and g hat, right? Zeta, that's the same thing. It's just definition. I just, I wanna get you used to that notation too. So this is 1 over the square root of 2 pi by definition. That's the definition of Fourier transform of e to the minus I x zeta convolution of f and g, and this is dx. Okay, so that's definition. I haven't done anything. I just applying my definition of Fourier transform. But now this guy has their own definition. That's the convolution. Okay, so the convolution I define it here, right? So I have to apply that definition. So by definition of convolution, I have to do the following. So 1 over the square root of 2 pi, and this is over the real number, right? Or minus infinity to infinity, either way. Over the real numbers, e to the minus I x zeta, and the convolution is 1 over the square root of 2 pi integral over r f of x minus zeta. Instead of zeta, I'm gonna just use y. X minus y gy dy dx. So this is the definition. Green. This is the definition of convolution. Okay, that's all that I had done. Okay, now I have dy here, I have dx. So this guy doesn't have dy, so I can put it inside of this integral. So I'm gonna take my 1 over the square 2 pi's outside. I'm not canceling yet because I'm gonna need it. So I get integral of r e to the minus x zeta f of x minus y gy dy dx. Okay, so That's what we have. E to the minus x theta f of x y dy dy x. So we have to do a little trick here. Nothing that you haven't done before in your calculus class. So remember, what do we want? We want to get Fourier transform of G times Fourier transform of F. So somehow we should be able to get here we're gonna try to get the Fourier transform of F. Okay. Yeah. So I have, but you see, I have x minus y. So if I want to take the Fourier transform of small f, I need this variable x minus y over here too. So I'm gonna make a little trick here. So I have x, but I don't have y, so I need to multiply. So let me make room. E to the minus axc, right? So I need to room. So I need to have here. I need to have. Let me put it on red. I had to have e to the I. Let's call it some theta y. Okay, so I'm going theta. Yeah, okay. If I put this theta y, let's put it there. Okay, so if I put it there, then I had to put the is negative. Okay, so let's put dy. This is dy dx. So I need to put e to the minus I theta y. I mean, it could be next to it. Okay, e to the I theta y times e to the minus theta y is 1. So I haven't done anything. I'm just trying to make, and this is dy dx. Okay, I'm just trying to see how can I get the Fourier transform of f out of this. So I keep going. I get 1 square root 2 pi times 1 square root 2 pi r and r. Then I accumulate this guy. If I factor minus I get x minus y theta times fx minus y, and then gy e to the minus I theta y dy dx. Okay, so what is this? So look at this. So I got e to the minus I theta x minus y fx minus y, but who is the variable? So I need here is the tricky part, right? I need the dy, the dx over here, not dy. So by Fubini's theorem, so remember there is a theorem in calculus 3 that you show that you can interchange dy dx. Okay, and we do it here, dx dy. So as long one of the integral exists, you can do this interchanging by Fubini's, using Fubini's theorem. This is calculus 3. So as you see, we use here calculus 3, calculus 2, analysis, variables, complex variables, all over the stuff. That's what this is a core class, okay? So it's not my fault. So, so here, notice then that you got 1 over square root 2 pi. Now you got this integral with dx, integral with dx. Now you got e to the minus x minus y theta fx minus y. Okay, and notice that because you interchange dx with dy, these guys, gy e to the minus iy, they can be taken out of the integral because this integral depends on x, not in y. So that's what we're going to do. So we're going to take those guys out. We got 1 over the square root of 2 pi. And now look at, I'm going to put my integral here. I'm going to take these guys out. So let me put e to the minus I theta y gy 1 over the square root of 2 pi integral over r of e to the minus x minus y theta f x minus y dx dy. Okay, so hold on. So we go here and then look at this guy. Okay, so this is an integral that if I do a substitution, so notice this y is just a constant. This y is like a number 5 because dx, this integral is with respect to x, right? So this could be just a number 5. So what I'm doing is what happens when you find the integral of a function. Let's say the function is centered at 0, right? But now, if you compare with the same function, you move it with center at 5. What is different? What is the difference between the area? Nothing. That's the same area. That's the same integral. You just translated 5 units to the right. In this case, y units to the right. So this integral is exactly the same that e to the minus ix psi f of x dx. And that's the Fourier transform of f. So this guy is 1 over the square root of 2 pi 1 over r e to the minus I theta y gy, and then this guy is the Fourier transform of f. Dy. But better than that, because now this is a function that depends on theta. It doesn't depend on y. So that one is a constant, so I can take it out. So I get f Fourier transform of this guy times 1 over the square root of 2 pi over the real numbers e to the minus I theta y gy dy. And now what is this guy? This guy is the Fourier transform of g. So this is Fourier transform of f times Fourier transform of g, as we want. So we just prove that the Fourier transform of the convolution is the product of the Fourier transform. So or if you want like this, f hat of theta times g hat of theta. Either notation is fine. I mean, I just like to use both notations. You just have to get used to it. Okay, so now I think we can stop this video now.